Okay, we'll look at a series of drag integrals here. We'll start with the easiest one. We have a cart, so no motor, pushed with an initial velocity vi, and then it's going to encounter a drag force as it goes, linear drag force, so linearly proportional to the velocity, and that's the only force acting on it in the horizontal dimension. That's what makes it easy. We're going to look at the graphs, and then we're going to look at the velocity and position functions. So the velocity starts at the vi that was given, and then it's going to slow down and asymptotically approach 0. That means the acceleration starts negative and fairly abrupt because it's going fastest, so the drag force is biggest, and then approaches asymptotically 0 as that thing gets towards the end. The velocity started pretty high, so we're going to have a pretty high positive slope at the beginning of the x-graph, and then it's going to asymptotically approach 0 because the zero slope rather, because the velocity value approaches 0. So we'll have something like that. Okay, so anytime you want to deal with these functions, you're going to start with an fnet. I'm always going to choose my direction, a positive being with the velocity. It makes your signs easier, and you don't have to worry about the v so much, because the v is actually a vector velocity. So it can be positive or negative. So it's always actually going to be negative bv, but it looks a little weird if your direction positive is the other way. And that equals m dv dt. And so in order to integrate, we need to get all the v's on one side and the t's on the other. I'm going to, as much as I can, keep everything off of the v side that I can keep off. So I'm going to divide the v under, leave that dv there, and then move everything else under. So minus b dt over m. And I integrate both sides. It's very important to know what your limits are and to actually faithfully use them. So I'm going to integrate from vi to a v of t, which is my vf. So it's going to be a function. It's going to be the velocity whenever I end my integral, which is t. This is a little bit sloppy notation here, but it's alright. It'll work for us. So I need to integrate both sides and then evaluate at the limits. So integral of this is negative b t over m, integrated from 0 to t, or evaluated from 0 to t. Integral here is natural log of v, evaluated from vi to v of t. Really important to take these limits. The left side is pretty easy because the 0 goes away, but this side doesn't. So natural log of v, or you could also call this vf if you want, but I like to emphasize that this is really a function that we're looking at. Minus natural log of vi, and vi is a constant. So you can either do your exponentiation now, or you can do it later. I kind of like to move this over. So natural log of v of t is natural log of vi minus bt over m, and I do exponentiate both sides. So e to the left side is just v of t, e to the right side, because these are added together, I multiply them. So that's vi, it's e to this, times e to the negative bt over m. So this makes sense because I started the vi, this is at c equals 0, this is 1, so my initial value is vi, and then this approaches 0, which is exactly what I expect it to do. So now if I want to find a position function from that, I need to do separation of variables again. So dx dt is really what v equals, which is vi, it's just a constant, e to the bt over m. So dx equals vi. This one's a lot easier because there are no x's in here explicitly. And I'm going to integrate from 0 to x of t as I go from 0 to time t. So this is just going to give me x of t, and this will give me negative mvi over b e to the minus bt over m, evaluated from 0 to t, very important. So I need to do negative mvi over b. Evaluated at t is just that. Evaluated at 0, this becomes 1. So I just factored out that negative stuff and put this in. Now I'm going to clean up the negatives. I'm going to just distribute that in. So mvi b times 1 minus e to the minus bt over m. That's my x of t function. So let's make sure that this agrees with our graph. Our graph starts kind of curvy and then ends up flat. As at t equals 0, this part here is going to be 0. Or I'm sorry, is going to be 1. So this on the inside is 0. So the whole thing is 0. So we start at x of 0, fine. As this gets bigger, as t gets bigger, this is going to get smaller and smaller. So this is going to approach the inside. This whole thing here is going to approach 1, which means this is going to approach mbi over b. So that's actually what our asymptote is. That's mvi over b. So this thing, even though it always approaches 0 velocity, it never quite gets there, it's not going to go infinitely far. It's going to approach also this position here.